All right, sorry about that. Can somebody post something on the live chat there, making sure that it's working? I think it wasn't working for me. I still feel it's not going to work. Something's off. Something's off. All right, I'm not seeing the live chat. So it is what it is. Not sure what the issue is. All right, anyways, I mean, we'll live with it for the day. I'm sure it's an issue with the website. All right, so let's get to work then. We were looking at series, tests for series. We looked at the integral test last time. Let's do a few exercises from there. We are asked to establish the convergence or divergence of the following. Maybe I'm going to try the. Here we go. I've toggled out the chat, and then it works. So that'll be it. We'll do that. Yeah, I refreshed the page as well. It wasn't working, but there it is. I've toggled it out. Looking good. Nikki is asking if we could. Nikki was asking to find a pattern of some sequence. I mean, it's not always possible to do that, right? Web work probably on Thursday after class. Sounds, yeah. All right, so consider this. Where n starts maybe at 1, right? So if we define the function x squared over e to the x cubed, right? This is the function that gave rise to this, right? For values of n, this function evaluated at n is exactly that. So we're hoping to use the integral test. We have to check that our function is continuous, positive and decreasing on the interval 1 to infinity. And of course, this is clearly seen to be bigger than or equal to 0. Continuous for sure, right? I mean, it's a quotient of continuous functions, and the denominator is never 0. Let's check for decreasing by taking the derivative. So this is a quotient rule applies. VU prime minus U V prime all over g squared. If we factor out an e to the x cubed, this leaves us with 2x minus 3x to the 4. So we can take one out, and if you factor out an x, this is 2 minus 3x cubed over e to the x cubed. And it's easy to see that if on the interval 1 to infinity, this is going to be positive. This is going to, I mean, for large values at least, well, in fact, you can show that from 1 onwards, this is going to be negative. So positive, negative, denominator is always positive. So the derivative is negative, which means that your function is decreasing. So we are in a position to use the integral test. Let's apply the integral test. The integral from 1 to infinity of x squared e to the x cubed, negative x cubed. This being an improper integral, you know what to do here. This is a limit. The integration is trivial. You can do that in your head. What do we get? Negative 1/3 e to the negative x cubed. Is that correct? And so this is 1/3e minus 1/3e to the n cubed. And as n goes to infinity, this goes to infinity. 1/infinity is 0, so this whole thing goes to 0, and we are left with 1/3e. The integral converges, so the series converges. Convinced? Charles is asking, if we find that the function is decreasing from a certain point onwards, can we still use the integral test? Indeed, you can, right? From that moment on. Absolutely. And as you know, with a series, the only thing that's important is the tail end of the series, right? It's the last infinitely many numbers. So the first few don't matter, even if it's the first million or 10 million terms, it's always going to be a finite number. The fact that we're adding infinitely many numbers is what's of importance. It's just the tail end of the series that we're interested in. Let's do a few more. Consider this. Let's rewrite that in a nice closed form. Right, what do we recognize? 5, 7, 9, 11, and so on. It's just the odd numbers, thank you. So 1/2n plus 1, where n starts at 2. There isn't just one right answer, right? Perhaps you may have wanted to describe this as 1 over 2n minus 1, where n starts at 3. That would have been fine as well. Nikki is asking, couldn't we have solved with L'Hopital's? L'Hopital's rule is not a test for convergence of a series. Using L'Hopital's rule will tell you that the sequence of stuff might converge. It won't give you convergence of the series. So let's look at the function which gave rise to this, 1 over 2x plus 1. Easily seen to be positive on the interval 1 to infinity. Continuous, right, because it's a rational function. And the only place you need to worry about is where the denominator is 0, which is at negative 1/2, not in this interval. And the derivative is easily seen to be minus 2x minus 2 over 2x plus 1 squared. The denominator is positive, the numerator is negative, so the whole thing is negative. Your function is decreasing. So we can apply the integral test. Let's do it. You have to justify. You have to justify that the function is decreasing. However you want to do that, but you have to justify. Let's look at the integral. It's an improper integral, you know how to deal with that. Integral is trivial here. You can easily see it to be this. I started at 1. I could actually have started it at 2. That would probably have been the better thing. Not that it matters, right? But we only had our series from 2 onwards. Of course, we do not need the absolute values here. And as n goes to infinity, you see what's happening, right? Ln of infinity is infinity. So the whole thing is infinity, i.e. the series diverges. We changed the 1 to a 2 because our series actually started at 2. So, yeah. Consider this. Again, let's rewrite it in a nice closed form. This is easily seen to be 1 over n root n, thank you. Or 1 over n, well, let's call it n root n. but let's take a moment to rewrite it as 1 over n to the how do we show what it converges to again? That's Sophie asking that. That's a very important question. And we don't. We don't. Right, let's take this example for a moment. This, what did we say, 1 over n to the 3 over 2? Thank you. This is the series 1 over n to the 3 over 2. And this is a special kind of series. As we defined it last time, this is known as a p-series. And what do we know from our class time? This is a convergent p-series. Where p, in this case, is 3 over 2, which is bigger than 1. And that's it. Convergent p-series, that's it. Now, to answer, was it Sophie? To answer Sophie's question, what does it converge to? We have established the series converges. Now, a very important question is, what does it converge to? Nobody knows. Nobody knows what this converges to. We know it converges. We don't know what it converges to. So now we can embark on that journey to try to figure out what it converges to. So you can do research. You can approximate it numerically, absolutely, and we're going to do exactly that in a moment. In the next question, somebody's suggesting that Professor Humphreys probably knows. I'm going to go on a limb and say that he doesn't, because if he did, this would be a very important result. So we can only tell what it converges to in geometric series. Well, I mean, geometric series is one very important case. We also saw some telescoping sums. Oh, I know you were joking, but still, though, it's still I knew you were joking about Professor Humphreys knowing what it converges to, but this is only to drive home the fact that nobody knows what that converges to, and it's an open question, right? So you can try to work that out. Well, I mean, it's not so important. I mean, I've given it perhaps more importance than it requires. But if you were able to work out what it converges to, somehow, this would be a new result and important enough to publish, and probably the way you would have proven it would probably have worked for other series as well. Why don't we take another example, right? We'll take one from the book, which does exactly the same thing, right? Consider this. We are asked to find the partial sum S10 of the series 1 over n to the 4 and estimate the error in using S10 as an approximation to the sum of the series. Right, so exactly what you were suggesting we do with that question. Let's do it with this one instead. I mean, it's the same process. So, regardless. Right? So, I mean, whether you're doing this or whether you're doing that, it's the same thing. So, what are they really suggesting here? First of all, understand that this converges. Why does it converge? How do we know that this series converges? So this is a convergent P series where P is equal to 4 bigger than 1. Exactly the same reason as before. Absolutely. So we have a convergent P series. We know it converges. The integral test doesn't tell us what it converges to, though. All it gives us is convergence. So now we embark on that journey to figure out what it converges to. We're not going to do that here. Rather, what we're going to do is approximate what it converges to. Because, you know, I mean, oftentimes with computers nowadays, an approximation is usually good enough anyways. All right. So how are we going to approximate? Well, we're going to add, right? I mean, this is an infinite sum. So we're going to add what is that? This is 1 plus 1 over 2 to the 4 plus 1 over 3 to the 4 and so on forever. We're going to add the first 10 terms. That's what S10 is, right? It's the partial sum. So we're going to add the first 10 terms. All the way to 1 over 10 to the 4. And then we'll be left with the rest. Right? So we can add the first 10 terms. And then we'll be left with the rest. And this is your S10. Right? The partial sum, the sum of the first 10 terms. So that's where a calculator or computer comes into play. Somebody want to work that out on Wolfram Alpha? Or shall I? Who's going to do it faster? Oh, Tiffany, thank you. Louis as well. Excellent. So Wolfram Alpha has given us that this is 1.08204 according to Louis. Thank you. And then you have some other stuff. And this, right, which is this, is equal to that. So you see what's happening, right? You see what's happening. If you bring this to the other side, right, this, your S10 here, if you bring it to the other side, you get that whatever your series converges to, we don't know what it converges to, but whatever it converges to, minus this approximation, is equal to that. So this is the error. It's the difference between what the series converges to and your approximation. This is your error. So now let's estimate the error. How good of an approximation is this? How close are you to the actual sum? Now, improving the integral test, we saw that we actually had a bit more. We saw that the proof of the integral test actually gave us a bit more than the statement of the test itself. And we saw, what did we see? We saw that the integral from k to infinity was less than or equal to the sum This is what we showed. Or, if you concentrate on this part, and now replace k with k plus 1, you can squeeze this term. Right? That term is less than or equal to that integral. But it's also bigger than or equal to, right? If you replace k with k plus 1 here, you have that sum is bigger than the integral from k plus 1 to infinity. And this is what you have. This is your error in using the sum of the first k terms. So in our case, in the case at hand, the sum from 11 onwards is less than or equal to the integral from 10 onwards, and is bigger than or equal to the integral from 11 onwards. So can we integrate these in our heads? This is going to be negative 1 over 3x cubed from 10 to infinity. And this is negative 1 over 3x cubed from 11 to infinity. So in other words, again, this is less than or equal to 1 over 3,000. And this is bigger than or equal to 1 over 3 times 11 cubed, whatever that is. And there you have it. Your error is sandwiched between these two values. Or, if you prefer, this, the difference between what the series converges to and your approximation is sandwiched between these two values. Or, if you want to add 1.08204 everywhere, you get a nice interval, a very small interval, in which this lives. This is going to be some number between these two numbers, which are very close together anyways. Can we make the bottom bound approach 11? I don't know what you're talking about. It is 11. Maybe you weren't, maybe you were talking about something else. Karim is asking how many terms does the initial approximation need to have for the approximation to be acceptable? Well, that depends on what you mean by acceptable. Let's do an example. Questions here before I erase some stuff? How are we doing with this? Isn't it from 1 to 10 and then 11 to infinity? Sure. So what's the final error? What was the question asking? Estimate the error. So the question was asking us to estimate the error, and the answer is the error, which is this, is somewhere between 1 over 3 times 11 cubed and 1 over 3,000. So let's say this, the error is somewhere between 1 over 3 times 11 cubed and 1 over 3,000. Somewhere in there, we have estimated the error. How did I get 1 over 3,000? Well, how did I get 1 over 3 times 11 cubed? It's the same thing, but with 10. Questions here? How are we doing? So how will we do this on a test? Because you need Wolfram Alpha? Well, I mean, the tests are online, so it's not an issue. And let me point out that nowhere did we really make use of this value to answer what the question was asking, right? The question was asking to estimate the error, and we have estimated the error here. And absolutely right. I mean, you can find S10 manually. You're just adding 10 terms. I mean, I'm not going to ask you to do that, but again, the point is, in this particular question, you did not even need to work out what S10 actually was. They wanted an approximation for the error, and we did not use anything for that. Tiffany is asking, how did we move around the comparisons to get to the squeeze part? I'm not sure what you, maybe here, from here to there. I mean, this part is just this, right? So I've rewritten this part right here, and then concentrate on this inequality, but replace k with k plus 1. So you get the sum from k plus 1 to infinity is bigger than or equal to the integral from k plus 1 to infinity, and that's exactly what I have here. All right, let's see another example. Here I'm adding 1.08204 to all three sides. If I do the same to both sides of an inequality, the inequality remains. Find the sum of the series correct of 4 decimal places. Very nice exam question. I can't see the picture very well. All right, moving on. Find the sum of the series correct of 4 decimal places. Well, I mean, the obvious question that arises, does this series even converge? And Tiffany is asking, does this mean we have to add up the first 10 terms or more than that, right? We don't even know. We don't even know how many terms must be added. And if the series doesn't converge, then, I mean, we're done. This question wouldn't make sense. So let's check. The function that gave rise to this is, of course, x over e to the 2x, which is positive. Continuous. What about decreasing? Take the derivative. VU prime minus UV prime all over V squared. Simplify that. Simplify that. What do we get? 1 minus 2x over e to the 2x. And it's easily seen to be negative if x is in the interval of 1 to infinity. Right, numerator is going to be negative, denominator is going to be positive. Dom is confused about the error. But are you, though? You know what that word means. This is going to converge to something. We don't know what. All we know is that it converges. What we're going to do is we're going to add some terms. We're going to add some terms, maybe the first 10 terms, as Tiffany suggested, but we don't know. We don't know how many terms we're going to need to add, but we're going to add some terms, and we're going to get an approximation. What we want to make sure is that the first 4 decimal places are correct. Exactly that. Yep. Ian, thank you. All right. So what do we say? Positive, continuous, decreasing. We can apply the integral test. And let's do it. My question to you is, how do we integrate? Well, Ali is suggesting that we can just add terms until the first 4 decimal places stop changing. But how do you know that you've added enough so that it never changes again? Integration by parts, thank you. So u is x, dv is e to the minus 2x dx, du is dx, and v is negative 1/2 e to the minus 2x. So this becomes uv minus the integral of v du so this is minus 1/2 n e to the minus 2n plus 1 over 2e squared. Antiderivative here. 1/4 e to the minus 2x from 1 to n. All right, here we go. If it's always decreasing, then it shouldn't vary after the first 4 digits are locked in. You're confusing what is decreasing. The terms are decreasing. The terms you're adding are decreasing. But the sum itself, right, because you're always adding more and more and more terms that are positive, the sum itself is going to be increasing. As n goes to infinity, this is easily seen to be going to 0. What about limit as n goes to infinity of this part, which is n over e to the 2n? Well, this is easily seen to have the form infinity over infinity. A quick L'Hopital's rule will give it to you. 1 over 2 e to the 2n, which goes to 0. So this goes to 0 as well, and we're left with this, which is 3 over 4e to the e squared. Converges, and we're good. So we know the series converges. So now we understand that the question makes sense. We can approximate what the series converges to. And what we want is to make sure the first 4 decimal places are correct. Now, the problem is we don't know how many terms we need to add. Right? So what are we doing? We are approximating the series, what is it? N e to the minus 2n. So what are we going to do? We're going to add some terms. We don't know how many. So let's say from 1 to n, big N. Now, of course, it's an infinite sum, so you'll be missing the rest. Right, so you're missing from n plus 1 to infinity. When do we know when to use the integral test, though? Well, you can use it when it applies, which is why we were checking for positive, decreasing, and continuous. If your function is positive, decreasing, continuous, you can apply the integral test. Right, so here's what we have. And if you bring this over to the other side, right, this is your Sn. We're left, of course, with this, which is your error term. The tail end of the series, right? The series from n plus 1 to infinity. Now, so this is going to be our error, right? This is the difference between what the series converges to and our approximation. Now we need the error. What do we want? We want the first 4 decimal places to be correct. We want these first 4 decimal places to be correct. What we're going to do, we're going to start somewhere. We're going to assume, we're going to make our error less than halfway further. This in no way guarantees that the first 4 decimal places are going to be correct. Example, if you take, suppose your approximation was 1.23456, right? Let's just assume that this was the approximation we got. If our error is equal to this, and you added them together, 2, 3, 4, 2, 3, 4, 6, 1. You see, it would change the 4th decimal place. So this would not be correct, but it's a starting point. Let's not worry about it for now. Understand that this is not sufficient in general, but it's only a starting point. Why are we doing n plus 1? Well, I mean, it comes from this, right? The sum from 1 to infinity is the sum from 1 to n, and then n plus 1 to infinity. Why not do it with 0.00005? I think that's what we're doing. Did you mean one more zero? In any case, whatever but it wouldn't matter. It wouldn't matter. It doesn't actually matter what you start off with. There's no number, however small, you can make the error such that it never matters. Right? No matter how small the number you give me here, I can give you an example where it's going to go south. Exactly. Exactly as suggested. If the approximation was 0.9999999, however many nines you want, but finite, no matter how small your error was, you'd still be in trouble. All right. So I think we have somewhat of an understanding. So only a starting point, and you'll see in the work that we have to adjust anyways. So now, from the proof of the integral test, we saw that this was less than or equal to the integral from n to infinity. So, can anybody confirm that this was the antiderivative? Are we back? Thank you. Can anybody confirm that this was the antiderivative? Pretty sure Suddenly I want to throw in a negative here instead. Negative, negative. Very good. So what is that? This is, I mean, when you plug in the b and you take a limit as b goes to infinity, it goes to infinity, and we are left with 1/2 n e to the minus 2n plus 1/4 e to the minus 2n, or (2n plus 1). Right. Where did b come from? It's an improper integral because of the infinity. I'm replacing infinity with b. I think in this case we have an n, right? All right, and now we want this to be less than 0.00005, and I'm going to let you, Philip, we're using this as a starting point, just as a starting point. You'll see what happens. Now, what I would like you to do is to verify that this is actually decreasing. I think it's pretty clear since it's almost essentially the same thing we had before. This is a decreasing function. You can take the derivative. Alexander doesn't understand why we're using the b. It's an improper integral. You know how to deal with improper integrals. Why do you have to verify that it's decreasing? Because if it's decreasing, as soon as it's less than this, then all the others are going to be less than as well. And that is a very nice property. But let's assume that it is. I'll let you prove it. And now let's do some trial and error. Somebody with access to Wolfram Alpha, can you verify what happens if n is 3? What value do we get here? No, Ali, we cannot. It's not going to work. Not going to work. Wolfram Alpha. Why 3 specifically? Trial and error. I have no reason to think that this is going to work. I'm going to do the Wolfram Alpha myself. If n is 3, that is 7. I'm way off. This is 0.00433. Not sufficient. If n is 4, I'll probably be off as well. That's going to be 9 over 4e to the 8. Three zeros and a 7. Still no good. If n is 5, is still no good. Unfortunate. I should have taken something bigger. One, two, three, 4 zeros and a 1. So close. 4 zeros. Wait, 4 zeros and a 1. I'm good. 4 zeros and a 1. Did everybody get that? Looking good. Find a 6, 4 zeros and a 1. Very nice. So Louis Charles had given us that as well. 9969. 9969. So you see, when n is 6, it's the first time we're less than that. So we're going to, well, I mean, what was the point of the decreasing? You know that since this is decreasing, as soon as you're less, then all the other ones are going to be less as well. So that's why you would want to show that it's decreasing. All right, so what are we saying? We're saying n should be 6. So now let's add from 1 to 6. And somebody use Wolfram alpha again. I'll use it. If you sum from 1 to 6 and e to the minus 2n, what do we get? 0.18, 185, 3297, and so on and so on. I assume some people have worked that out already. Very nice. Oh, 52, 53. What slightly did I misread it? $185. Well, I think yeah, all right. We're good. I think Gabriel had missed an 8 here. No worries. This is our approximation. The error is this. So if you add or subtract the error, is it going to affect the first 4 decimal places? That's the question. Our error, 4 zeros, 1, 2, 3, 4, and a 1. And you see what happens, right? You see what happens. If you add, there's no issue. This is going to turn into a 2. But it's not going to affect that. But if you subtract, If you subtract, you're going to need to change this into a 9 and a 1, and it's going to affect, in fact, it's going to affect the third and the fourth decimal place. So we're in trouble. We're actually not in trouble here. We're actually not in trouble, but we could have been. In the sense that the series is only made of positive terms. So you're not going to be subtracting anything. You're never going to be larger than what the series actually converges to, right? You're only adding the first 6 positive terms. So this is never going to be bigger than what it should be. But things could have gone awry. That's all I'm saying. So the error is going to be less than or equal to that, and consequently, it's not going to change the first 4 decimal places. So Nikki wants me to repeat why it's not going to be an issue. Let me convince you another way. And let's do it in general. So it'll make a lot more sense. The stuff we're adding is bigger than 0. So this stuff, which is equal to the sum from n plus 1 to infinity. Right? This is your error, as we've established a long time ago. Right? It's the difference between what the series converges to and your approximation. Now we have made this less than or equal to 0.0000199. But here you're adding stuff that's positive. So this is always going to be bigger than or equal to 0. So you're never actually going to subtract anything. It's always going to be positive. So your error is at most this thing. That's not a convincing argument. Let's say this. What do we have here? This is 0.18, 108 stuff. So let's rewrite this thing. We have the sum from 1 to infinity of n e to the minus 2n minus and that is less than So now if you add this to all sides, so what do we get? This is going to be a 2. So 18, 10, 2, 8, stop, blah, blah, blah. Here we go. That's a lot more convincing, right? So the series, what the series converges to is some number between these two. And you see that the first 4 decimal places are the same. There it is. All right. Nicholas is asking, since you're using Wolfram Alpha, can't you just pick a random number like 20? And if that satisfies our condition, can we keep it? What's your condition? What's your condition to keep it? Well, I mean, fine. But first of all, how do you know that adding the first 20 will give you an error less than 0.00005? You don't know that. This is very dependent on the actual function. Gabriel suggests you could have used Wolfram Alpha to solve for the inequality. Absolutely. Yeah, that's fine. Exactly. Yeah. Well, I mean, it's actually not that long. I mean, here we're taking a lot of time, and I'm answering questions and this and that. But if you know what you're doing, there's no reason to spend more than 10 minutes doing this question. So 10 minutes in a 3-hour exam, you still have a lot of room for other questions. So what is the answer? The answer was looking for the first 4. It was looking for an approximation correct to 4 decimal places. So this would be a correct answer. This would be a correct answer. All right, let's move on. Nikki is asking if it could be negative, what will we do to fix the issue? We'll get to that later on. Let's move on. Let's move on to the comparison test. Let the series A AN and the series BN be series with positive terms. Where AN is less than or equal to BN. If the series BN converges, then the series AN converges. If the series AN diverges, then the series BN diverges. Let's look at the proof. Proof is very nice and easy. We have this inequality. AN is less than or equal to BN. So if you add these terms, the inequality remains. And since you're adding terms that are always positive, there we go. So what? If the series BN converges, what does it mean to converge? It means that this approach is a finite number. In other words, that this is less than infinity. If the big one is less than infinity, then the small one is less than infinity. So if the big one converges, the small one converges. Similarly, if the small one diverges, what does it mean to diverge? It means that the sum is infinite. If the small one diverges, then the big one is bigger than or equal to infinity. So the big one has to be infinity as well. If the small one diverges, the big one has to diverge. And there it is. Simple to prove, simple to state, somewhat difficult to apply, because you have to establish this inequality. And that's always a little bit of work. Luckily, we have a simpler version, if you will, known as the limit comparison test. Don't read too much into it. Let's concentrate on the somewhat difficult to apply. It's not difficult, it's somewhat difficult. Because again, you have to establish an inequality. Limit comparison test, very similar to the comparison test, but there's no inequality to establish here. Let AN and BN be series of positive terms. And suppose the limit of one divided by the other exists. If L is bigger than 0 and less than infinity, then both converge. Both series converge. or both series diverge. Let's do a few examples. Before we do a few examples, why don't I give you a flavor of the proof? What does it mean for the limit to exist and be some value L? This means that for large N, AN over BN is very close to L. So for large N, AN is going to be approximately L times BN. So the series AN is going to be approximately L times the series BN. So if this converges, then that one converges. And if this one diverges, then that one diverges. In other words, they behave more or less in the same way. As long as L is not zero, nor infinity. Let's take a few examples. We are asked whether the series converges or diverges. Consider this. So what are we going to do? Well, you're thinking to yourself, if the 1 wasn't there, if the 1 wasn't there, then this would be an easy question to deal with. This would just be a p-series. But we do have the 1, so it's not a p-series. But for large values of n, this 1 is insignificant. So for large values of n, this series kind of looks like 1 over root n. So this suggests a limit comparison with a series 1 over root n. And what do we know about this series? This is a divergent p-series where p is 1/2, which is less than or equal to 1. Let's apply the limit comparison test. This is limit of one of the terms divided by the other. You're dividing by a fraction, we're going to multiply by the reciprocal. Factor out a root n from the denominator, perhaps. Or you could do a L'Hopital's rule, because they both have, and this looks like an infinity over infinity. These cancel out nicely. As n goes to infinity, this goes to 0. So we're left with a limit of? We're left with a limit of 1. 1 is bigger than 0 but less than infinity. So both series converge or both series diverge, but this series diverges, so that one diverges as well. Anthony is suggesting, wouldn't it be easier to use a normal comparison test here? Perhaps. Shall we try that? See what happens? Let's try. And what am I going to say? I'm going to say that we already know what the answer is going to be, right? We already know that it should diverge. So we're going to, oh, I mean, I don't want to say cheat, but we have an advantage. We know it diverges. So in this case, we have to find a smaller series which also diverges, right? We have to find a smaller series which diverges. It's tempting to use the series 1 over n. But what's the issue here? As you know, -1 is less than or equal to 0. So if we add root n to both sides, we have this. And if you multiply the whole inequality by 1 over root n minus 1, which is positive, so the inequality is maintained, what do you get? What do you get? You get 1 over root n is less than or equal to 1 over root n minus 1. And what do we know about this series? The series 1 over root n diverges. It's a divergent p-series. So the series 1 over root n minus 1 diverges by comparison. Very nice. Couldn't you tell that by inspection? In this maybe easy case, yes. But let's never tell anything by inspection. You have to establish an inequality. And that's the slight difficulty with the comparison test. Robert was asking what happens if L is less than 0. This never happens. Because think about what's happening. AN and BN are both positive. So the smallest the limit can be is 0. Which section can we work on the error exercises that, I mean, they're all over the place, but in particular, this was the integral test we were looking at. By inspection is just by looking. Isn't it obvious that this is bigger than that? Well, maybe it is, but let's not go there. Do we have time for one more? Let's do one more. And then we'll call it a day. I don't know about you, but I feel that we're going very slowly here. Anybody else feel that way? It's like we're not covering any material almost. Why does dividing two divergent sequences give a finite number? I mean, it doesn't always. It doesn't always. But when it does, it means that they behave in the same way. Today was fast? All right, let's do one more and we'll call it a day. Now, when I look at something like this, I'm thinking to myself, for large values of n, how does this behave? For large values of n, the dominating term in the numerator is n itself. This minus 1 here is insignificant when n is very large. Similarly, in the denominator, when n is very large, this positive one is insignificant as well. So this, right, in other words, the denominator behaves like n cubed, the numerator behaves like n, so the whole thing is going to behave like a 1 over n squared. So we're going to do a limit comparison with the series 1 over n squared. And what do you know about the series 1 over n squared? Can't we use the critère du polynôme? I don't know what that is, so the answer is no. No. We're going to prove that it converges. We're not going to assume anything and use shortcuts. You're going to prove everything. So we're going to do a limit comparison with the series 1 over n squared. And what do we know about the series 1 over n squared? This is a convergent p series where p is equal to 2, bigger than 1. All right, so let's do a limit comparison. So one of them divided by the other. It doesn't matter which one goes on top, which one goes on the bottom. It's one divided by the other. So you know what to do. Flip it. You've got infinity over infinity. You can do L'Hopital's rule, or let's factor out an n from here and an n cubed from there. Either way, it'll give you the same answer. The n cubes cancel out nicely as n goes to infinity. This goes to 0, this goes to 0. So the whole limit is 1. 1 is bigger than 0, but less than infinity. So both series converge or both series diverge. This one converges, so that one converges as well. Can we just observe that 1 over n squared is bigger and converges, interesting. So, I mean, I would expect you to prove that, but I think it's easy to prove as well. So you can do that, absolutely. And you get convergence by the comparison test. Very nice. Could this also be a telescoping sum? Interesting. It might have been. I don't think it is, though. I'll let you work that out, but I don't think it is. How are we doing here? Questions? So work on this. We'll do a few more next time and then move on to other series. Other series, other tests. Absolutely, right? I mean, the remainder business, it's non-trivial. It takes some getting used to. Wrap your head around that. Do some exercises. We can discuss that again next time if you have questions. The limit is 1. 1 is bigger than 0 and less than infinity. This is the criteria for the limit comparison test. So the conclusion is that both series converge or both series diverge, but we're working with a convergent p-series. So this one has to converge as well. The limit comparison test tells you that both series behave in the same way. Either they both converge or both diverge. We started with a convergent one, so the other one has to converge as well. All right. Thank you all for coming. I'll see you guys on Thursday. Still haven't posted office hours yet. Still very, very busy with other things, but they're coming. Email me if you've got questions.